All right, so I've kind of started to talk about this 18 electron rule, and I just want to mention a little bit about why this is actually important. Why is it important that we do have to know how to count electrons? I know it sounds crazy to have to do that, but the reason why this is so important is because when we are starting to involve those organometallic complexes and coordination complexes in general in catalytic reactions, we need to be able to know how many electrons our complex has as a starting point to be able to know if we will be able to add a ligand to it. So if we don't know how many electrons a complex has, we will not know if that complex can actually have another ligand added to it, or if it would have to lose a ligand before something else can be added to it. Okay, so we have this rule that is called the 18 electron rule, and the rule is very general in the sense that it says that most of the organometallic compounds, they tend to obey the 18 electron rule, which means that they tend to have a maximum of 18 electrons. That's what it means, okay? Which means that when you count the total number of electrons, usually, right, it should not be, this number should not be higher than 18, but it does, if it does have more than 18 electrons, that means that we will not be able to add any other ligand at first. We'll have to, first of all, remove one of the ligands, and then being able to add that ligand that we want to be, part of the final compound. They are, and I don't want you to think that all organometallic compounds have 18 electrons. It's not, a rule that is always obeyed. Some of these complexes are actually going to have less than 18 electrons. They can have 17 electrons, they can have 16, and actually some of the early and late D block metals will form complexes which will have 16 electrons. So like the iridium, the rhodium, the palladium, and then the platinum complexes, they tend to actually only have a maximum number of valence electrons equal to 16. Okay, so that's why we need to know what those counting rules are. We need to be really proficient in terms of doing this, otherwise we'll have some issues down the line when we're going to start involving those complexes in catalytic reactions, because remember, the fact that those organometallic compounds are so special, it's because they are involved in a lot of catalytic applications among a lot of other biological applications too. Okay, so the first counting rule that is really important and that actually simplifies our life is that we assume that the metal center is a zero valent metal center. So we don't look at the charge on the metal center. We consider, that the metal center is just, a zero valent metal center, which means that we're going to look at iron 0, we're going to look at rhodium 0, we're going to look at manganese 0. We are not taking the charge into account. And obviously you know that the number of valence electrons from the metal is the group number, okay? So that's what happens. So we pretty much are simplifying our lives here. And then we need to make sure that we know how many electrons the ligands are providing. So I have a list here of how many electrons are being donated. Some obviously of the counting is kind of self-explanatory, right? I don't have to tell you that, for example, a hydrogen can only give one electron. I'm not saying a hydride, right? I'm saying a hydrogen, but usually you'll see hydrogen giving one electron. Even if it's just a hydride, it's hydrogen. The terminal chlorine, bromine, iodine, and the alkyl, or the pretty much even a phenyl group when it's in a eta 1 hapticity, it will pretty much just be a 1 electron donor. Okay, so everything that is terminally bound will be 1 electron donor. The when we add obviously more elements to the ligand, such as carbonyl, the phosphane, here there's an example of a phosphite, right? So the phosphane has been oxidized, or any of the eta 2 alkenes, right? Carbene, which means we have a double bond. Anytime when we actually have more elements, here we have carbonyl, we have phosphanes, we have eta 2 alkenes, we have 2 electron donors. Okay, We just covered earlier on an example of the allyl ligand, which means that it was eta 3. Eta 3 means that it donates 3 electrons. The carbine, so we don't have just 2 double bonds in a carbine, we have an alkyne with 3 double bonds. That's an eta 3. Obviously also hapticity, so we have a 3 electron donor here, as well as the bridged chlorine, bromine, iodine. Those are bridged ligands, right? So they provide 3 electrons, and those are just the bridged, the mu bridged. We'll see later on that the mu 3 bridged ligands actually give more electrons because there's more bonds, right? We've seen the typical example of an eta 4 ligand, which is the eta 4 butadiene ligand, which means that it gives 4 electrons, and that's the most common one. We've also seen an example of an eta 5, the cyclopentadiene ligand, giving 5 electrons. So that's when it actually has the hapticity of 5. Remember that cyclopentadienyl does not have to be in the eta 5 mode. It can also be in the eta 1 and the eta 3. That's why it's important, right, to mention the hapticity and to have the correct hapticity, because otherwise we are not going to be able to count those electrons correctly. Okay, and then eta 6, as you can imagine, right, if a cyclopentadienyl ligand with 5 carbons in a ring can give 5 electrons, that means that when we have a phenyl group C6H6, it can bound in an eta 6 manner. Okay, so I think, these are the main ligands that we're going to be using, and pretty much the ones for which I want you to know how many electrons are donated. But there's one specific ligand here that we are going to be using, that is NO. And there's something very specific about this ligand, because depending on how many bonds are formed between the nitrogen and the oxygen, we can either have a 1 electron donation or a 3 electron donation. So let me explain to you what that means. So when we are looking, for example, at a, so we have a metal, and then we have a nitrogen, and then that's NO, right? If we have here, I only have 1 bond, right, obviously between my metal and my nitrogen. Here my nitrogen is hybridized 1, 2, 3, it's hybridized sp2. If the nitrogen is hybridized sp2, right, it's going to be only giving or donating 1 electron. If, on the other hand, my nitrogen here is forming 1, 2, 3 bonds with the oxygen, and obviously only 1 bond with the metal center, right? My nitrogen here has a full octet. It's only hybridized 1 and 2. Remember, multiple bonds are not taken into account in hybridization. So my nitrogen here is hybridized sp. If my nitrogen is hybridized sp, it's actually a 3 electron donor, because some of the electrons that are part of the triple bond here are ultimately going to end up being on the metal center. Okay, so if we have a nitrogen hybridized sp2, we have a 1 electron donor. If we have a nitrogen hybridized sp, we have a 3 electron donor. So it is very important when we draw those structures, right, to be able to distinguish the double bond here from the triple bond, because, well, the hybridization changes, therefore the number of electrons is also changing. So we'll see how that plays a role when we actually get to not just the counting of electrons, but most importantly chemical reactions, organometallic reactions involving this ligand NO. Okay, so let's apply, right? Let's do a little bit of practice here, and let's apply those counting rules. So let's turn the page here and look at what we have. So what I'm going to do here is that I'm going to do the first 2 complexes with you, and then I'm going to ask you to do pretty much the rest of the complexes for Wednesday, and on Wednesday I'll give you the answers to those other complexes. I think I have a total of 6 organometallic complexes here for you to look at, and the question is pretty simple. It's just count the total number of valence electrons, right, to see if these organometallic complexes are applying the 18 electron rule, or if they don't. Okay, again, I don't want you to think that they all do. Okay, there are exceptions, but in general they want to obey that 18 electron rule. So remember the first thing that we need to look at. So here is our famous molecule of ferrocene. Remember, this is the sandwich molecule. This is the metallocene that has an ion in the center. And that ion in the center is pretty much sandwiched between two cyclopentadienyl ligand. One bond, two bonds, right? My eta 5 cyclopentadienyl here are represented from the point of view of having the ion bound right to the center here of that circle. That's how I show that I have an eta 5 cyclopentadienyl ligand. Okay, so the first thing is that I usually do is that I draw the molecule and then I start counting. So remember, we are assuming that the metal center is zero valent, right? Zero valent means that we don't have any charge. So I know here we don't have any charge, but even when we will have some charge complexes, we are not going to be including the bond, the charge in the counting of electrons. So we always count metal centers having zero, pretty much, or being zero valent, which means they don't have a charge. Which means that we need to go back in the periodic table, right, and look at how many electrons we have for iron. We have 8. And then we have 2 ligands that are eta 5, right? So we have 2 eta 5 CP, which means that each of the cyclopentadienyl ligand gives 5 electrons. So when we count, right, we have 10 plus 8, that's 18. So we have a total of 18 valence electrons. The ferrocene molecule obeys the 18 electron rule. Okay. We are going to complicate things a little bit and add different types of ligands on the metal center, which here in this second example is rhodium. So I have rhodium in the center, and the first thing that I always look at, right, is how many ligands do I have. So this is one ligand. This is my eta 5 cyclopentadienyl ligand. This is my eta 2. This is my eta 2 ethene, right? This is an alkene, carbon-carbon double bond here. So eta 2 gives 2 electrons. And then this is a phosphane ligand with pretty much a phosphorus with 3 methyl groups on it. Okay? So I have 1, 2, 3 ligands, which means that this molecule here is going to be trigonal planar. So I can't draw a molecule without knowing what the shape is going to be, right? Here it's pretty simple for the ferrocene molecule because I only have 2 ligands, so it's a linear molecule, okay? But here I have 3, so it's trigonal planar. So I'm going to have 1, 2, and 3 bonds from my rhodium to those 3 ligands. It doesn't matter where I put those ligands. What matters is that I really show what the hapticity looks like, and I show the correct bonding, which means that, for example, if we start looking at my cyclopentadienyl, my bond goes from the center of the circle here to the rhodium. My eta 2 alkene, which is ethene, right? Remember, it goes pretty much from the middle of the bond here to the metal center. I don't have to represent the hydrogens unless you want to. And then finally, I have a trimethyl, Me for methyl, so trimethyl phosphorus. We actually say trimethylphosphine. So this is just the metal center will be directly connected to the phosphorus in this ligand. And then you can say, you can put it this way, or you can just say trimethylphosphine. Okay, it doesn't matter. Okay, now the goal is to be able to count those electrons, right? So the first thing I look at is the metal center. It's rhodium 0. Rhodium has 9 valence electrons. The cyclopentadienyl ligand has a hapticity of eta 5. So it provides 5 valence electrons, or it donates 5 valence electrons, or 5 electrons. The eta 2 here, my eta 2 C2H4 provides 2 valence electrons. And then finally here, the trimethylphosphine, right? Phosphines in general are providing 2 valence electrons. Okay, so when we count here the total number of valence electrons, right, we have 9 and 9, that's 18. So I have 18 valence electrons again in this complex. Okay, all right. And that means that, so, you know, if you recall, right, when I first introduced the organometallic chemistry unit to you, I said, well, ferrocenes and especially metallocenes in general do have lots of applications, and especially in catalysis. So that means, though, if we want to add something on this complex here, if we want to add a ligand, we can't. We are not able to add a ligand, another ligand to the metal center, if we don't get rid of one of these cyclopentadienyl ligand first. So before we can add to this and do more synthesis with it, we have to remove pretty much that cyclopentadienyl ligand first before we can add more to it. Okay, all right. The same thing here is true with the rhodium. Since I already have 18 electrons, I'm already at the maximum number of electrons, we are going to have to remove one of these ligands first if we want to add something else. Okay, all right. So what I want you guys to do for Wednesday is that I want you to look at the other complexes. They are, I believe, 1, 2, 3, 4 more complexes to do, and we'll go through the answer keys on Wednesday, and that's pretty much the last topic that is on the study guide for the quiz on Friday, is the 18 electron rule, right? It's just pretty much knowing how many electrons are donated, and knowing what pretty much the hapticity stands for. So it's pretty straightforward, but let's do more practice, and I will have the answer keys posted also on Canvas for the practice problems that I'm asking you to do, which are listed on the cover page of that Unit 5. All right, you have a wonderful day. I'll see you on Wednesday, if not before. All right, have a good one.